Okay, who gets a packet? Now, some of you are not going to be here, I understand. Right? Chai, every time, there's something wrong, Chai. Okay, who gets a packet? Walk. Window. Jen. Now, I saw the list, there's 2 people missing, right? Sign and Saito? So you guys better keep up because this is the hardest chapter of the 4th quarter. You guys picked the wrong time to go on the trip. That's okay. Watch the video, do the problem, but the problems are not, these problems are like, oh, some of them is going to blow you out of the water. So you better hope that somebody asks those questions so they're on the video.
That's all the questions.
What? No, in the lobby.
No, it's no Wi-Fi.
Where is this? In like Shanghai? That's racist.
What's the trip for?
What hotel are you at?
Some business.
History? Business?
Then go to Starbucks. That's what I do. And I don't even drink coffee.
What are these signals?
You just go to Starbucks so you can use your computer.
There aren't Starbucks. Oh, I see that.
Okay, how about you just go to Starbucks just to download the videos, and then when you go back and then save it, and then when you go back to the hotel, then you can watch it.
Can you download?
Of course, right?
I'm asking
Yes,
questions.
you can.
Ask after class.
How come? No, then you tell me why on my computer why I have so many videos stored from YouTube.
Yeah, because download it from your camera.
No.
You can
From
download.
no. Okay, this is what I did. I go to Google and download video from YouTube, and they have instructions, and I just copied it. I just did what it said to do. And it was easy too. You just click something, and then boom.
What chapter is this again?
What?
Series.
Series. Okay, now just as a review, what did we do last chapter?
Sequences.
We did sequences. Now we're gonna do series. What's the difference? Well, I already told you the difference, but you guys just don't remember. 2, 5, 8, 11, 14. This is a sequence. What kind of sequence is this? Arithmetic. Now, what if I were to add the terms of a sequence?
Series.
Now it's a series. Sequence, series. Do you see the difference? Okay, let me boil it down for you. A sequence has commas. A series has plus signs. By definition, a series is the sum of the terms of a sequence. Now, of course, if you learn series, then you have to know sigma notation, which we already went over in the 2nd quarter. But period 6 didn't remember anything. Okay, so let's review sigma notation. K equal 1 to 6, k squared. Okay, so this is your formula. What number do I start plugging into that formula? 1. What's the next number?
2.
And you go all the way up to
6.
6. So you're starting with this number. You plug in consecutive integers until you hit that one. Okay, plug in 1.
1.
Plug in 2,
4.
3,
5.
4,
16.
5,
5.
6. And the sigma is the Greek letter for
Addition.
S.
S.
The Greek letter for sum. It's the Greek letter for S, which stands for sum. So you add up these numbers. Doesn't that just make sense? Sigma. Now, a lot of people, when they first see this, they say E. If you say that in college, you can be laughed out of. That's worse than saying Euler. That's worse. That's sigma. This is the uppercase sigma too, and then you got the lowercase sigma, right? We know from pre-algebra. We use this for standard deviation. That's because you were in the other class sneaking. Oh yeah? Well, everybody else took it in pre-algebra. right? Sigma, standard deviation. Okay, whatever. Okay, so what if I were to ask you, write this series using sigma notation? Okay, now today's lesson is just a review of what you learned last year. Tomorrow things get kicked up a notch, as you will find out. Okay, so the first thing you do is you write the sigma. How many terms are there here? 1, 2, 3, 4, 5. So you go k equal 1 to 5. And then what is the formula? What is the explicit formula that'll generate these numbers? So now it's just like sequences, right? What's the explicit formula for this sequence here? Ooh, it's arithmetic. The common difference is 3. So you write 3n and then you adjust. If you plug in 1, you want to get 2. Minus 1, and there you go. That's how you write in sigma notation. So you have to know your skills from sequences, right, to write the explicit formula. The sigma just tells you to add them up. Yeah.
Would you put 3k? Would you change the k?
Oh yeah, I'm sorry. It's a K. Thank you. Only one person noticed that? The rest of you just nodding. No, it doesn't matter. You can use whatever dummy variable you want here. If you want to use n, you can use n. The two most common ones are in math books are n and k. But if you want to be fancy, you can be fancy. How about j? Is that fancy? Whatever, it doesn't matter. As long as the variable is consistent, like the one I wrote there wasn't, right? So it didn't even make sense. Okay, now, how do you add... Okay, let me erase this. So, if you have an arithmetic series, okay, let me just give you another example. Sigma k equal 1 to 100, 5, no, 6k minus, give me a number, 3, no, 5. Okay, what is this equal to? Compute this number. See, this is what's going to be on the next quiz, which is probably Friday. Yeah, probably Friday. Okay, what's the first thing you should do? Plug in a few numbers, just like when you did sequences, right? Plug in numbers. Plug in 1, 2, 3, what do you get? 1 plus 7 plus 13, and you keep on adding up until you get to, what's the last number you plug in? 100, what do you get? 595. Okay, now compute this. Add up 100 of these things. Now luckily for you, there's a formula. If you look in any Algebra 2 book, or if you look at my notes, you will see this. The sum of the first n terms in an arithmetic series is equal to n over 2 times first term plus last term. Now you know where this came from? Okay, let's go back to elementary school. Did I tell you the story of Gauss already? Gauss. Remember I told you, who's the 3 greatest mathematicians of all time? Archimedes, Gauss, and Sir Isaac Newton, right?
How about that other guy?
Euler. He's number 4. Euler is number 4, and then you got a whole bunch of other guys down there. Pythagoras,
No, no, that's someone else.
Euclid,
Isn't it
Descartes, Galois.
There's like some guy that did some kind of.
Why am I even writing over here when we're videotaping? Okay, 1 plus 2 plus 3 plus dot dot dot. Anyway, when Gauss was a young child, he was going to school and the teacher got mad at the class. So he said, I want you to add all the integers. This is in Germany. I want you to add all the integers from 1 to 100. Does that sound German?
No.
So he figured the students would take all morning to do it, but Gauss was very clever for an 8-year-old. He goes, ooh, if I add the first with the last, you get 101. If you add the second with the second to the last, you get 101. If you add the third with the third to the last, you get 101. So shouldn't the answer be 101 times 50? Because there's 100 numbers here. Every time you pair them up, you get 101. There's 50 pairs, right? And so the answer is just going to be 5, 0, 5, 0. And so Gauss did it in like 30 seconds. And the teacher got even more mad. But that's where this formula came from. See, this is an arithmetic series. To find the sum of an arithmetic series, you just count how many pairs you have, n over 2, And then you multiply that by the first term plus the last term, which is what you're doing over there. So that's where this formula comes from. Okay, so let's do a problem then. Now that you know where this came from,
But where'd you hear that story from?
I read books. That's what I do, I read math books. You see all those books, you can't see, they're out very back. I have dozens and dozens of math books.
So you
I love to read books about math history. That's what I do. I don't,
So you read like his biography.
no, but he's mentioned all over the place. Come on, I'm pretty sure that's in your pre-algebra book. Okay, so how many terms are there here? I'll give you a hint. Look at this number here.
100.
From 1 to 100, there's 100 terms. So using this formula, it's going to be 100 over 2 times the first term plus the last term. Boom! You get 3 out of 4 if you write that on your paper and you want the last point, you got to compute it. But that's easy. You just go 596 times 50, right? Everybody can do that. Okay, so that's arithmetic series. Now, what about geometric? Well, we know what a geometric sequence is, right? A geometric sequence has a common ratio. Arithmetic sequence has a common difference, okay? So what if you have this, okay, 3, comma, 6, comma, 12, comma, 24, comma, 48. What the heck, let's go one more. Okay, this is a geometric sequence. If I add the terms of the sequence, you get a geometric series. Write this series using sigma notation. So when you go sigma, k equal 1 to, how many terms are there? 6. And how do you write the explicit formula for a geometric sequence? Remember the formula? Okay, let's review. A sub n equal a1 r to the n minus 1. Come on, you just took a test last week, man. Okay, so what's the first term? 3 times, what's the common ratio? 2 to the n minus 1. Finished. So you just write the explicit formula like we did last chapter, and you just tack on the sigma, because the sigma just tells you to add them up. Okay, let's do another one. Okay, let's go the other way. I give you the sigma notation. Let's use n this time. N equals 1 to 10 of 5 times 2/3 to the n minus 1. Okay, first of all, before I even start, how do I know this is a geometric series? Because when you have a number to the nth power, remember that's geometric. Okay, I'll give you a hint. Let me spell it out for you. If you see something that looks like this, whatever's in the parentheses, that's the common ratio. Okay, if you don't believe me, okay, let's write out the first few terms. Plug in 1, go. Plug in 1. 5. Plug in 2. Plug in 3. 29. All the way up until you hit plug in 10. Oh, you guys are in trouble, yeah? Okay, you know what? Maybe that's too mean, yeah? Okay, let's just go to 6 then. You guys can't handle. Let's just go up to 6 then. Plug in 6. 5 times, what's 2 to the 5th? 32. Well, you know what? Let's go up to the 7. Let's go up to the 7. What's 2 to the 6th? 64. And what's 3 to the 6th? 729. So that's going to be 320 over 729. There you go. Okay, now add up these 7 numbers. Now, you could, if you wanted to write out all 7 and add them up, you can, but luckily we have a formula from algebra 2. The sum of the first n terms of a geometric series is? Anybody? A1 all over 1 minus r. That's how you find the sum of the first n terms of a geometric series. So if we apply it to this problem, what's A1, the first term? 5. 1 minus, what's the common ratio here? What do I keep multiplying by? Yeah, the number in the parentheses, people. 2/3 to the n. How many terms am I adding up? 7. All over 1 minus 2/3. So whatever this number is, that's the answer. Well, luckily you have a formula. Otherwise, Can you imagine adding 7 of these up? You gotta make least common denominator. Some of you just, there's no way already, yeah? Okay, now let me change the problem just a little bit. What if I were to keep adding forever, like infinity? Now we call this an infinite geometric series. Now I already taught you about this, right, when we studied probability. How do you find the sum of an infinite geometric series, remember? First term over 1 minus r, but the absolute value of r has to be less than 1, otherwise the series diverges. In other words, it doesn't add up to some finite number. So, what is the common ratio in this problem again? Here, again, look at the number in the parentheses, people.
Plus than 1.
It's 2/3. Is the absolute value of 2/3 less than 1? Wait, let me get my calculator. Yes. So therefore I can use this formula. So, if I keep on adding these numbers forever, you will get the first term, 5, all over 1 minus the common ratio, which is 2/3. So 5 over 1/3 is 15. If you keep on adding these numbers forever, you will get exactly 15. Exactly. Is that mind-blowing for some of you? It's just like, you guys don't really understand infinity, because look, in pre-algebra, didn't you learn that 0.9 repeating is 1?
Yes.
It's not approximately 1, it is 1. Okay, anyway, I think you guys are confused because you just don't have a good concept of infinity. Some of you still think infinity is a number. Okay, so here's something Mr. Masunaga taught you guys when you're in geometry to help you understand infinity. Did he teach you, who had Mr. Masunaga? Then you guys learned hotel infinity then, right? How come the period 6 told me they learned that in Mr. Masunaga's class? I'll give you something. Okay, here's the hotel. This is called hotel infinity because it has an infinite number of rooms.
Oh, we did,
Right, of course. Okay, but there's a sign. The sign is up. It says, no vacancy. What does that mean?
Not vacant.
Very good. It's not vacant. That means all the rooms are taken. All the rooms are filled. There's no room already. All the rooms are filled. You guys get it?
Oh.
But there's an infinite number of rooms. See, that's the key. So I come to the hotel. I'm tired after a long trip. And I go, okay, can I get a room? And then the guy goes, no, I'm sorry. All the rooms are taken. So I said, here, why don't you do this then? Try this. The person in room 1, move him to room 2. The person in room 2, move him to room 3. The person in room 3, move him to 4, and so forth and so forth. I will take room number 1. Yes, sir, very good. You have room number 1. Can you see why that works? Because there's an infinite number of rooms. It doesn't end. Like if there was 100 rooms, then you cannot put the person in room 100 into 101 because there's no room 101. But since there's an infinite number of rooms, you can just keep pushing them down.
Why can't you just push him?
What?
If there's an infinite number of rooms, why don't you just put him at the end?
But there is no end.
Or instead of pushing everyone down.
Okay, just do what I do. Okay, now, just when you think you know better, look. What if here's a bus. This is a bus. This is the infinite bus because it has an infinite number of people in it. And this bus drives up to Hotel Infinity with an infinite number of rooms, but they're all taken. So the bus driver goes in, the tour leader goes, oh, I need rooms for my passengers here. Can you get me a room? He goes, oh, no, I'm sorry, we're all booked. And so the bus driver says, take the person in room 1, move them to room 2. Take the person in room 2, move them to room 4. Take the person in room 3, move them to room 6. Take the person in room 4, move them into room 8. Take the person in room 5, move them into room 10. You guys get it? And so on, forever. And we'll just take the odd numbered rows. Okay, very good, sir. Here's your keys. You can do that because there's an infinite number of rooms. I think we're going to have problems in this chapter. Okay, anyway, so tonight's homework is just arithmetic and geometric series. That's all it is. So these are the typical problems that you see. Okay, I didn't do this for another class, but I'll do it for you guys.
Is there gonna be a whole to infinity problem?
You never know. Did everybody here take the test? Who didn't take the test? You just never know, because remember on the test, the Fibonacci sequence thing, huh? Just when you thought you didn't have to know.
I took a picture of that.
Okay, here. Okay. This problem, every single Algebra 2 book, you can pick any Algebra 2 book off the shelf. This problem is in it. You drop a ball from a height of what? 12 feet? Okay? Every time it hits the ground, it rebounds to a height that's what? Half the previous height then. Okay, so 6. Then it goes down 6. Then it bounces up half of the previous height. 3. Then it goes down 3. Then it goes up 3 halves. It goes down 3 halves. Then it goes 3/4. 3 down 3/4, and then it just keeps doing this forever. How far did the ball travel?
Forever.
So is the answer infinity? No. Now there's lots of ways of doing this problem. One way is you could count, okay, this is the typical way. You could count all the down arrows, and that forms an infinite geometric series. And then you can add up all the up arrows, and that forms another infinite geometric series, and then you just add the two together. But if you're clever, you do this. Add these two, these two, these two, these two, and so on and so on. And that forms an infinite geometric series. So what's the sum of an infinite geometric series? First term, 18, all over 1 minus r. Half, 36 is the answer. If the ball keeps bouncing up and down in this manner, it travels exactly 36 feet. Exactly.
36 feet up and down.
Yeah, up and down. So this is the infamous bouncing ball problem. So you can group it any way you want. Some people, like I said, some people do all the up arrows and then they do the down arrows. So anyway, I just wanted to show you guys this once. Now, are you guys looking at your homework tonight? I think one of the problems on the homework tonight says quiz next to it. You know why? Because that's going to be a problem. The exact problem you're going to get on the quiz sometime either at the end of this week or at the beginning of next week. I'm just telling you what the quiz is ahead of time so you can research it or practice it on your own. So everybody can get 20s on it. But then why is it that every year some people get zeros? Anyway, what does it say? Quiz. Find the perimeter and area of the Koch snowflake. And it's Koch now because it's named after the mathematician Helgi von Koch. Helgi von Koch. Because the other period 6, they're going the crotch snowflake. It's not even funny. It's the Koch snowflake. Now what the heck is the Koch snowflake? Well, this is what you start with an equilateral triangle of side S. Remove the middle third of each segment and replace it with another equilateral triangle. Then you do it again. Remove the middle third of each segment. Replace it with another equilateral triangle. And then do it again and again and again and again ad infinitum. In other words, keep on doing it forever. So, if you look on the bulletin board over here, see, here's the snowflake curve. So after one iteration it looks like that, then after 2, 3, 4, 5, and 6. So your job is to find the perimeter and the area of the Koch snowflake. That's what the quiz is. And you can't just say the answers. You gotta show me how you get the answer. Now this is what normally happens. They go on the day before the quiz or the morning of the quiz, they go on the internet, they Google Coke snowflake. And then they try to memorize the stuff that's up there, and then when they get the paper back, it's 0. Because they memorize things wrong. Instead of memorizing, you don't even have to memorize, just do it. All you have to know for this is infinite geometric series. That's all you gotta know. Infinite geometric series. And I'll give you a hint. Okay, you have to find the perimeter and the area. One of these is infinite. Which one do you think it is? Why can't the area be infinite?
It's in the same space.
How about this? Does that circle I just drew have an area?
Yeah.
Yeah, and that curve is inside the circle. So therefore its area gotta be smaller than the area of the circle, right? So therefore the area cannot be infinite. So, yeah, but you can't just write that down. You gotta show me or explain to me how it's infinite. Okay, anyway, that's a quiz that you're gonna get next week. See, at least I'm telling you ahead of time. Okay, let me pass back the test. How much time we got? 13 minutes. Okay, I've got to turn off the camera.